knows a lot about the science stuff. Professor Dave explains.
In the previous tutorial, we described the Suzuki-Miyaura coupling reaction as the most widely used approach to palladium-catalyzed CC cross-coupling, and we also briefly mentioned some other related reactions. If the Suzuki reaction is unsatisfactory, even under the most favorable conditions described in the literature, the next best approach to try is the Stille reaction. The Stille reaction is the cross-coupling of alkenyl or aryl halides with organostannanes, and bears its name from John K. Stille, who worked at Colorado State University and is responsible for the broad exploration of this important reaction. In the reaction, R1 and R3 are usually alkenyl, aryl, or heteroaryl, but alkynyl and allyl groups also participate. R2 is an organic group, usually methyl or N-butyl, often called a dummy ligand because it is usually transferred much more slowly than their alkenyl or aryl counterparts. The major advantage of the Stille reaction over the Suzuki coupling is the fact that it can be carried out under completely neutral conditions. We saw that the coupling of boronic acids needs an excess of hydroxide ion to activate the palladium. This is not the case for stannanes, which couple directly without further activation, usually at elevated temperatures. Organostannanes are very stable compounds, which can be distilled or chromatographed, and in fortunate cases even crystallized, and are therefore quite easy to handle. One minor drawback of the Stille reaction is the competitive transfer of the dummy ligands, especially methyl, but even the less reactive N-butyl. It is not unusual to find small levels of 4, often under 10%, in a typical coupling of aryl stannanes with aryl halides. The Stille reaction, due to its neutral character, is a very popular tool in complex total syntheses of natural products. A striking example from the work of Professor Amos Smith at the University of Pennsylvania is represented by the total synthesis of rapamycin, an important immunosuppressant, in which the intramolecular Stille coupling is the last step in the synthesis and is shown not to interfere with the complex functionality of the molecule, which includes epimerizable CH functions. The Stille coupling is much less used in industry. The main reason for its scant industrial applications is the formation of the co-product trialkyl tin halide. Unlike the Suzuki reaction, which produces boric acid, easily removed by an aqueous wash, the Stille coupling forms trialkyl tin halides which are organic soluble, and are retained in the organic phase after workup. Tin halides have a certain level of toxicity, and they have to be completely removed from the product, which is not a trivial task. There are many methods to accomplish this, including a wash with aqueous fluoride, which precipitates the tin halide as highly insoluble trialkyl tin fluoride, but usually product crystallization is necessary to remove all the tin. The best current protocol to carry out the Stille reaction is a method introduced by Professor Gregory Fu, who was working at MIT at the time, but who is currently at Caltech. The main innovation is the use of the ligand tritert-butylphosphine, a bulky ligand which binds to palladium-0 twice, but to palladium-2 only once due to its steric bulk, leaving the fourth coordination site open for the stannane. The second innovation is the use of fluoride as a promoter, usually as a cesium salt. These conditions allow couplings with iodides and bromides at room temperature, and even chlorides, albeit at elevated temperatures. An example is shown here. The mechanism was elucidated by Professor Annie Jouton at the École Normale in Paris. The main oxidative addition product, in the presence of a large excess of fluoride, is tricoordinated complex 5. As we mentioned, the ligand is so bulky that the fourth coordination site at palladium is vacant. It is then quickly occupied by the stannane via a metal-pi bond coordination, and in this intermediate it is postulated that the fluorine atom also coordinates with the tin atom, thereby facilitating the formation of the tin fluoride leaving group and formation of the palladium-carbon bond. The tin is eliminated as trialkyl tin fluoride, which precipitates and can be filtered off. The catalytic cycle is terminated by the reductive elimination, yielding the product and the catalytic palladium-0 species. As for the Suzuki coupling, many other bulky ligands can replace tritert-butylphosphine, including the already mentioned very popular Buchwald ligands, 3 of which are shown below. Like for the Suzuki reaction, the coupling of alkyl halides works poorly with palladium catalysts, and is best run using nickel catalysts. This modification, also invented by Professor Fu, requires an equivalent of tin tetrachloride. It is believed that the reaction proceeds first by transmetallation of the trialkyl stannane 8 to trichlorostannate 9. Species 9 is then the probable transmetallating species under nickel catalysis. An example is shown here. As with the Suzuki coupling, the catalyst requires bidentate nitrogen ligands, and the catalyst load is rather high, up to 15 mol%. However, this extension of the Stille reaction has great practical potential, and the search for more stable and active nickel catalysts is ongoing. Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.